Okay, hi there. So, sorry, I'm a couple minutes over. There was some sort of an issue with the stream, but it seems to be working now. Um, Good evening, everybody. Thanks for stopping in. I'm going to have the chat open. I'm going to go through some problems. Let's see what we can do tonight. For those of you that don't know, I am StatProf 5000. Most of you are probably coming from my Discord. Otherwise, you probably have liked and subscribed some of the videos on our YouTube page from Responsive Analytics. If that's the case, I appreciate it. So why don't we jump into this? So let me just talk a little bit about why I decided to do this and how this is all going to work. So over about the last week, I've been getting questions that people want to see done in terms of how to do them with the statistics. What I've done is I've compiled 4 of them that I'm going to go through tonight. If I don't get to your question, and obviously we don't have all night to do this, I'm going to save some time at the end for question and answers. Hopefully we can get through some of that during that session. So let's get started. So the first question that I'm going to do is what you see here on the screen. This is a question. This is a normal distribution type question, and somebody submitted this to me earlier on in the week. One of the reasons why I chose this normal distribution question is most questions that you see that are like this, they'll give you a mean, they'll give you a standard deviation, they'll give you some information, and then they'll just say things like, what's the probability that x is bigger than this? Or what's the probability that x is less than this, or at most this, or at least that? The nice part about this particular question is it gives you some of that information, but then it puts you in a scenario, and then you have to be able to see that, all we're really asking still are those simple, this is greater than that, this is less than this type questions, but you have to weed that out of the question itself. So let's start with this. What I'm going to do is I'm going to talk to the question a little bit, then I'm going to use StatHelper to get us to the solutions, and then I'll go through exactly how you deal with these different things. Okay, so let's start. So the question that we have here first is, suppose the force acting on a column that helps to support a building is normally distributed with mean 15 KIPS and standard deviation sigma equals 1.25 KIPS. Okay? So then we get the information the column will be stable if the force is between 12 and 18 kPIS. Anything outside of that is considered unstable. So this is actually similar to a lot of the normal distribution problems you see, but the last couple of sentences make it a little bit trickier. They're giving us a mean, they're giving us a standard deviation, they're giving us some numbers that are important for certain reasons. Okay, so let's take a look at some of these questions. The first question basically says, what's the probability that the column is unstable on the high side? The second question says, what's the probability that the column is unstable on the low side? Part C says, what's the probability that the column is stable? And Part D asks, the engineer would like to know what value does 95% of the data fall below? So when you're dealing with these normal distribution type questions, there's really 2 different ways that this can be done. You can be either given a specific x and want to know a probability that that x could occur, or I could give you a probability and then I want to know the x that it corresponds to. For this question, we're really getting both. Okay, so let's dissect this a little bit. Part A says the probability that the column is unstable on the high side. If we go back to the question, it basically says the column will be stable if the force is between 12 and 18. That means in order to be unstable on the high side, what we need to have happen is we need to basically find out if basically x is going to be greater than 18. Okay, that's what we're looking for Part A. because we know if it's outside of 12 to 18, it's unstable, and 18 is to the high side. That being said, part B says what's the probability that the column is unstable on the low side. We know the low side here is going to be less than 12, so we're going to say what's the probability x is less than 12. For part C, it says what's the probability that the column is stable. Now, there are a couple ways we can look at part C. It says right in the question that the column will be stable if the force is between 12 and 18. So we can look at the probability that it is greater than 12 but less than 18, or we can basically take the probability that it's greater than 18 plus the probability that it's less than 12 and take that value and subtract it from 1. Okay? Because remember, when you're dealing with probabilities, everything has to sum to 1. Okay? So if it's less than 12 and it's greater than 18, if we basically sum that together and subtract it from 1, we will get what's in between 12 and 18. Okay? And then finally, what we're doing here is we're trying to find the value for x such that x less than or equal to some value x is going to be equal to 0.95. Okay, so that's what we're going to do with these 4 problems. I'm going to show you how you can do this in, I'm going to use the stat helper to get us there, and then we'll discuss the solutions. Okay. As we go through this, if you have questions, comments, please don't hesitate to put them in the chat. Okay, so now we're going to go to the stat helper. Okay, so in order to get to the stat helper, where you're going to want to go is you're going to want to go to apps.responsiveanalytics.com, and I will post that either in the chat or in the comments below, or both. So we've got, what I'm going to do is I'm going to go to Stat Helper Plus. Okay. So it's launching here. Okay, so you're here. We're going to need to log in. So I'm going to say statprof5000@gmail.com. That's my login information. And then I'm going to put in my password. And I need one more 0 here. There we go. Okay, so when you go into the stat helper, what you're going to see is you're going to see this welcome page, and then on the sidebar here we have all of these different types of things you can do with it. Okay, we're going to focus for now on probability distributions, but when we get to some of the problems later on, we're going to do hypothesis tests, confidence intervals, we'll use descriptive statistics, etc. So we're really going to be using these top 4 modules tonight. Okay, so because I'm looking for probabilities and values with a normal distribution, I'm going to go and I'm going to click probability distributions. Okay, and notice here it does have, it's set up in terms of tabs. Okay, the first tab that you're going to see is a notes tab, and it's just going to give you some general information about probability distributions. We are interested in the normal distribution. Okay, now once you click in one of these, you're going to have all these different tabs. You'll have description, tips, examples. Up to this point, these are all populated. If you click on any of these, you will see Pac-Man. Okay, the reason is because it's waiting for data to populate those tabs. Okay, so I've had students in the past and people in the past that use this say, aren't you worried about, you know, you're using Pac-Man, isn't that restricted? I said, well, they can send, Nameco can send me a cease and desist letter if they want. So I'm going to click start. Now, one other thing you should know about the stat helper is everything's predicated on start and reset. Okay, so I'm going to click start. Okay, and then I'm going to open a window like this. I'm going to click input the mean. Our mean was 15. Input the standard deviation, which was 1.25. Now, I've had some questions in the past about sample size. Sample size really is just, in this particular case, is just 1 because we're dealing with a single observation or a single random variable. Later on, when we start dealing with averages, that's when the sample size will change. But for right now, let's keep the sample size as 1. Okay, let's go back here and look at the problem. Again, the problem part A says, what's the probability that the column is unstable on the high side, which means that x is greater than 18. Okay, so let's go back here. That means we want greater than. Now, another thing you should notice here, when you go up to the select probability symbol drop down, you only have 3 options. You have less than or equal to, greater than or equal to, or between 2 numbers. And the reason it's set up that way, and you don't have less than or you don't have greater than, is because the normal distribution is continuous. So there's no mass at a point. Okay, so less than is equal to less than or equal to, and greater than is equal to greater than or equal to. Okay, so we're going to pick greater than or equal to because we want to know what's greater than 18. We are looking for a probability, not an x value at this point. Okay, we know the x value. The x value is 18. Okay, so input the mean, input the standard deviation, sample size. Those were all given in the problem. We know we're looking for greater than. Okay, again, because we want to know unstable on the high side, and it's unstable if it's outside of the 12 to 18 range. Okay, so we've got probability because that's what what we want for our outcome, and now we have 18. So let's click run. Okay, now what you're going to see here is we're looking for the probability that x is greater than or equal to 18. Okay, now everything, because of the way the typical z table is set up, everything is set up to focus on less than values. So you can see what I did here. As I'm looking for greater than 18, I'm converting that into a less than value by doing 1 minus less than or equal to 18. Okay, and you see that pretty much with most probability distributions that you deal with. Okay, so we're using the z table. It's given us less than values. When you deal with the normal distribution, what you do is you convert your situation from x to z, and we do that using this z statistic. Okay, that's going to be x minus x bar over the standard deviation. Okay, we input the value for 18 for x, 15 for x bar, 1.25 for the standard deviation. That gives us a z value of 2.4. Okay, now normally what you would have to do at this point is you have 2 options. Either you have the computer that has the z distribution built in, okay, or you have to use a z table. Okay, and what you're going to do is you have to go look up 2.4 and figure out what probability that corresponds to. Okay, if we come up here, we do have something called the z table, and you can see what it does is it highlights your 2.4 here, and the third value is going to be 0. So what it does is it goes down, and then it basically tells you that the probability that corresponds to 2.40 is 0.9918. Okay, go back here to the work. So what we found is the probability that x is less than or equal to 18 is the same as the probability that z is equal to 2.4, and that gives us 0.9918. Okay, now what we're going to do is play plug and chug back into this equation. Okay, 1 minus 0.9918 gives us 0.0082. And you also see here that we can visualize this based on the curves. The full probability for the normal distribution equals 1. Less than 18 equals 0.9918. Subtract those two, and it gives us this small value to the right of 18. Okay, so for number 1, part A, the answer is 0.0082. Okay, so are there any questions that anybody can think of on what I just did? I'm just writing in the chat to please post any questions here. Okay, so I'll wait a second just to see. Okay, so hi Rachel, thanks. No questions. Okay. Okay, Joseph, thanks. No questions. Okay, so what we'll do is we'll do parts B and C. They're both very similar in how they work. I'll show them to you with the solution so you can see what's happening, but I won't do them in as great a detail as what we just saw. Okay, so part B says what's the probability that the column is unstable on the low side, which we were going to find the probability that x is less than or equal to 12. We're going to come back in here. We're going to reset our inputs. We're again going to put in the mean equal to 15. Standard deviation is 1.25. Okay, now we're looking for less than or equal to. We're still looking for probabilities, right? Because here we're looking for the probability that it's less than 12. Okay, so basically everything's the same here, except now instead of looking at greater than, we're looking at less than. And less than problems are usually a lot easier because you don't have to deal with subtracting 1 or anything like that. It should come out directly. Okay, so we basically follow the same path. Probability x is less than 12. Plug and chug into this z formula. You end up with minus 2.4. Okay, we then go to the table and we can get our probability, which is 0.0082. If you want to take a look at how that came out, we're looking at negative 2.4, so we come up here 0.0082. Okay. And then here, this is actually 9918. This answer is 0.0082. Okay, so pretty straightforward, same essentially as what we did for part A, except for we basically said now we're looking for less than 12, right? If we look at that, here we find here's 12, we're getting less than that. Remember, the previous question gave us 18 over here in this situation, okay? One was unstable on the high side, one was unstable on the low side, okay? Now, we're looking for what the probability is that the column is stable, okay? So we saw earlier that it says here, the column will be stable if the force is between 12 and 18. So it's that extra step you have to be able to do is going from, okay, I know what stable means, so I can backtrack from stable in part C to realize from the question that that means we want between 12 and 18. Okay? So what we can do is go here to reset again. Again, 15, 1.25. Now what's going to change here is we're going to change this from less than to between two numbers. Okay, we're still looking for probabilities. The smaller number here is going to be 12. Larger number here is going to be 18. Okay, so all I'm doing here is basically saying I want you to find the probability between two numbers, and those two numbers are 12 and 18. Click Run. Okay, now if you think about this, to find the values between 12 and 18, what we're going to do is we're going to look at the probability for less than 18, subtract off the probability of less than 12, and then you end up with what's in the middle. Okay. What you're going to need to do in order to do this is find the z for 12, which we already found was negative 2.4. Find the z for 18, which was positive 2.4. Then we're going to find the probabilities from the table that they correspond to. One is 0.9918, the other is 0.0082. Now, if you look at the z table here, it actually does both. So we come down here to negative 2.40, we come down here to positive 2.40, and we get our two probabilities. Okay? Now, sometimes faculty or instructors will want you to use the table. Sometimes they just let you use the computer. It should work either way. You find those two probabilities. What we're going to do is subtract them, and we're going to get 0.9836. Okay? So in this case, there's a 98.36% chance that the column will be stable. Okay? And a lot of times when we look at problems like this, part C here would be the real world answer, right? Because most of the time people are going to want to know, okay, what's the chance that it's going to be stable? Hopefully it's really, really high, right? And in this case, we found it to be 98.36. Okay, now, here's another question. Okay, for those of you that are here, how do you feel about that percent in terms of a column that's supporting a building? Okay, to me, that is a little on the low side. Okay, I would want a column supporting a building that I'm in to be a little bit higher in terms of stability than the chance only being 98.36%. Okay. Okay, then let's look at part D. Now, what I found in the past is students have the most problems with this part of the question. Okay, because what you're doing is you're running everything in the reverse. If you think about what we've been doing in this particular problem so far is we take our x, okay, we go to our z equation, we play plug and chug. We have x, we have the mean, we have the standard deviation. And then we find z, we find our probability on the table. What we're going to do is work backwards. We're going to take our probability from the table, have that get us z, and then do some algebra in the z equation to get back to x. Okay? One thing you have to be really, really careful about is the fact that a lot of times what people will do is they will take this value and they will plug that in as the value for z. That is not z, it is the probability. You have to convert it from a probability to z based on the table. Okay? So let's take a look. We're going to reset. I'm going to go to start. Again, 15. Again, 1.25. Now, we're not looking for a probability anymore. We're looking for a value. Okay? And we're going to leave this as less than. Because if we look at this, we should see that the engineer would like to know what value does 95% of the data fall below. Okay, below means less than. Okay, so we're looking for x here that gives us a value of 0.95 for the probability. Okay, so the given probability, I'm going to put in 0.95. I've got my less than. I've got my parameters, 15 for the mean, 1.25 for standard deviation. Now let's click run. Okay, so you can see we're looking for the value of x that leads to a probability of 0.95. What you're going to do is you're going to go to the table and try to find a value on the probabilities that is as close to 0.95 as possible. What we found is 0.9495. Let's go take a look. Okay, we come down here, we find 0.9495. Okay, that ends up being 1.64. Now, our z now becomes 1.64, and now we're going to play plug and chug and do some moving around to solve for x. So we're going to come back here. Here's our z statistic. If we basically rearrange and solve this for x, we end up with this equation that you see here. Okay, we know sigma, 1.25. We know n, which is 1. We know the mean, which is 15. We found the z statistic from the table that corresponds to a probability of 0.95. That gives us 1.64. Okay, go through and do all our calculations here, and you end up with x equal to 17.05. So the value that 95% of the data fall below is actually going to be 17.05. Okay, and you can see here by the picture of the bell-shaped curve that 95% of the data fall below 17. Okay, so we would say here this little x is equal to 17.05. Okay, so for number 1 here, we really had 4 different parts, and this is pretty much what a lot of these types of questions will look like. The only thing you really didn't see here that you might see is maybe they want to know the probability that it's unstable. Okay? And for something like that, you can look at the probability that it's greater than 18, look at the probability that it's less than 12. Okay? That's the probability that it's outside. Or you can look at the probability that it's inside and then subtract it from 1. Okay? That kind of thing. Okay. Anybody any questions about that normal distribution type problem? The key to doing those kinds of problems is you have to be able to convert between the z value and the probability, and you have to understand when you're looking for which. Other than that, it's really just a lot of plug and chug with the z formula. Okay, and those types of problems, it's going to tell you somewhere that the data comes from a normal distribution. Okay, if there aren't any questions, then what I'm going to do is I'm going to move on to the next question. Okay, so number 1 kind of brings us to the question for number 2. It's very similar, but it's you're looking more at what we call sampling distributions. Okay. Number 2 basically says, suppose that the number of parking tickets for parking on the street given out on average in a month is 512. Suppose that we sample 256 weeks, and the average number of parking tickets for parking in the street per week is found to be 130. Okay. So think about the situation that we have. Okay. It's thought or it's known that on average we get 512 parking tickets per month. Okay, so that would be what we would consider the true parameter value, okay, for the mean, which is 512. Now what we're going to do is we're going to take a sample and we're going to try to assess how good that sample reflects on what we think the mean is. Okay. Now there's a few twists and turns in here because the mean is given per month and the samples are given per week, so you're going to have to do some adjusting to get everything in terms of the same units. Okay. Now, okay, there's a couple things you should realize about this problem. The number of parking tickets for parking on the street, okay, is actually what we would consider count data. Okay, so what that means is basically that this is a Poisson distribution. Okay, so X comes from a Poisson distribution. Now, we also know that for a Poisson distribution, we have one parameter. That parameter is lambda. And in this case, lambda equals 512 tickets per month. Okay? Now, that's solely when you're dealing with X, okay, just to give us what we call the underlying distribution. Another thing that you should realize about the Poisson distribution, okay, when you deal with the Poisson distribution, the mean is equal to lambda, but the variance is also equal to lambda as well. So lambda equals mu, let's call it mean, which also equals variance, okay? And that'll come in handy in a little while. Okay, now let's go down to the questions. The first question basically says, how many parking tickets for parking on the street would you expect to be written per week, assuming that there are 4 weeks per month? Okay, so all this really is doing is having you get the mean, the true mean, which is 512, in the right units, okay? So what we would do here is we would basically say, if I have 512 per month, okay, and I know that I have 4 weeks in a month, then when I divide them out, I'm going to end up with essentially 512 divided by 4, which equals 128. Okay? So what we're saying here for part A is basically that there are 128 tickets per week given out on average for parking in the street. Okay, now that's great. Okay? And all we really did there was use the fact that we wanted to turn everything into the same units. So now we have the mean is equal to 128 per week. We have a sample of size 256 weeks. We have a, within the sample, we have an average number of parking tickets for parking in the street per week being 130. Okay, now, we are now going to start talking about sampling distributions. A sampling distribution is the distribution essentially for the average for our particular random variable. Okay? Our random variable is the number of parking tickets for parking on the street. Okay? That would be what we would consider X. Okay? We have to get the sampling distribution of X bar. Okay? We know that the distribution of X is Poisson with lambda equal to 128 tickets per week. Okay? But when you start dealing with the sampling distribution of X bar, this is where what we call the central limit theorem comes into play. Okay? And if certain criteria are met, then X bar comes from a normal distribution with mean equal to mu and standard deviation equal to sigma over the square root of n. Okay? Now, one of those situations is that the data comes from a normal distribution, okay, and you know the variance, okay? We know here the data does not come from a normal distribution, or at least we're not given it, so we can't assume it, okay? The other way that you can use the central limit theorem here is if n is bigger than 30 and you know the parameters for the underlying distribution, okay? Now, this is where what we looked at earlier with the Poisson distribution comes in. Now, most of the time when people see this problem, and I've given it so many times, okay, most of the time when people see this problem, they say, Prof, this doesn't make sense because we don't have a variance. And I say to them, wait a minute, okay, what distribution does X come from? Well, I'm not sure. Okay, well, what is the variable? It's a count. Okay, well, then it comes from Poisson. And we know from the Poisson distribution that lambda is equal to the mean, but lambda is also equal to the variance. So, since a sample size of 256 weeks is bigger than 30, and we know the mean and the variance because we know lambda, what we can say here is X bar comes from a normal distribution with mean 128 and variance 128 divided by 256. Okay, so before I go on to part C, it's very important that you have an idea of where I came up with that. Okay, remember, lambda is equal to the mean, and the mean in this case is 128. Okay, lambda is 128. The variance in this case is equal to lambda divided by n, which in this case would be 128 divided by 256. Okay. Does anybody have any questions about this situation before I move on? If you do, please post something in the chat within the next couple of seconds. Okay? If you're not sure and you want to hear me again, talk to how I came up with the answer for part B. I need to get the Jeopardy music for when they're doing the Final Jeopardy in here. Okay, so I'm not seeing anybody come in with any issue, so we will just move on. Okay, so here's where you're using the sampling distribution. Okay, so part C says, what is the probability that you get more than 130 parking tickets per week for parking on the street on average? Okay, so now think about what we've got. We know the distribution for X bar. Okay, we know the sample mean, we know the variance, we know the standard error of the sample mean. Okay, or we know the standard error in general. Now, since we know the normal distribution, we can actually do this just like we would any other normal distribution problem. Okay, so here's what we're going to do. We're going to go in here, we're going to calculate Z in the same manner that we did before. Okay, here's the difference. Here's your Z-score. Okay, now the only difference between our situation and this one is instead of having X sub 0 here, what we're going to have is X bar sub 0, which in our case is 130. Mu in our case is 128. Okay, looks like we got a question. Rachel, go ahead. Okay, so Rachel asks, the variance in this case is divided by n. This doesn't happen all the time, correct? So, yes and no. Okay, so if we're dealing with 1x like we saw in the first problem, n is just 1, so it goes away. Okay, so in reality, it ends up just being x0 minus mu over sigma, just because n goes away, because it's 1. Okay. When we start dealing with problems with X bar, n is based on the sample size that we drew to get to X bar. Again, yes and no. You can look at this in two ways, okay? We can, once you divide it by n, we can plug that in, or we can use sigma equal to 128 and then n equal to 256, and you come out with essentially the same answer. Okay, so let me go to how we're going to put the data in, and I will show you what I mean. Is that okay? Okay, so remember here, we had to put in the mean, standard deviation, sample size. Okay? Now, there are two ways you can do this. Here, we can put this in as 130. Okay? We can put this in as 130. Then we can put this in as 256. Okay, or excuse me, 128, not 130, 128. And then put this in as 256. Okay, or what we can do is basically divide this out and then put it in. Okay? It just depends on the way you want to do it. Wait, I'm sorry, not 128. This is looking for standard deviation. So we would be putting in the square root of 128. So let's take a look at what that would be. We wouldn't be putting in 128. We would put in, this would be 11.3137. Because the stat helper is looking for the standard deviation. Okay? If you wanted to put in the standard deviation divided by the square root of n, okay, and then just call this sample size 1, you could do that as well. It all depends on what you want to put into this particular box. If you want to put in the adjusted, you can do that. Or because of the way the stat helper is set up, you can put in the actual standard deviation and then put in the sample size. Okay, either way will work. Does this make sense, or do you want me to go back to the Word file and talk to it a little bit more? Okay, good. All right. No, it's fine. Okay, so basically what we were trying to do here is basically see, okay, what's going to happen here in terms of how we input the z. Okay? So what I'm going to do is I'm going to input 130. I'm going to input 11.3137. And then I'm going to input 256. Okay, we are looking for greater than, or I'm sorry, yes, greater than, and this is going to be 128. Okay, now we'll put in 128. Okay, we should be able to run this, and what we end up with is we're looking for greater than 128, and we're going to have 1 minus less than 128. Okay, calculate that z statistic, and you end up with negative 2.83. Okay, so for the less than 128, you end up with negative 2.83, and go to the z table, and we get this less than probability to be 0.0023. Okay, since we're looking for greater than, we're actually going to play plug and chug with this, and what we end up with, just like the previous problem where we did the greater than, we do 1 minus, and we end up with 99.77. Okay, so the answer here, we come back here and we say the probability that you get more than 130 parking hours per week for parking on the street is, on average, is 99.77. Okay, so what we saw here is really a situation where you don't have data that comes from a normal distribution, but because of the central limit theorem, we can still use the normal distribution because we're dealing with averages. And what you'll find is that happens most of the time. Now, one thing that we really need to discuss a little bit is the idea of when the central limit theorem works and when it doesn't. Okay? There is a misnomer about the central limit theorem that people think as long as n is bigger than 30, then everything's normal. Okay? That only works if it's either it's already normal, okay, and you know the variance, or, excuse me, it's bigger than 30 and you know the parameter values for the distribution. If I give you a set of data and you just say, well, n is bigger than 30, so I can use the central limit theorem, that's not correct. Okay? You have to basically be able to show that one of those two conditions are met, right? Either it's normal and you know the variance, or you don't know the distribution, but you know the parameter values. In this case, it only worked because we knew lambda was 512. Okay? Okay, so really what 1 and 2 have done is gotten us ready to look at hypothesis testing. Okay, so the last two problems that I have for tonight are based on a one sample hypothesis test, and or excuse me, a one sample hypothesis test / confidence interval, and then I'll also do a two sample hypothesis test. Okay. All right, so let's look at number 3. Number 3 here is a question, and it basically says, an engineer is doing a study in a manufacturing setting on the lengths of staples. Okay? The sample that was collected is on a worksheet called staples, and I'll show you that data in a minute. Okay? Assume that the target value for staple mean length is 6 millimeters. Okay? He would like to see if the assumption still holds. Does it? Check this at alpha equal to 0.05. Now, you should be able to see that this is a hypothesis test. And the reason that it is because we basically have something they're calling an assumption, and we make the assumption. The assumption in this case is that the mean length of staples is 6 millimeters. And now they're asking you if the assumption still holds. Okay? Then, if you can't get that it's a hypothesis test from all of that, this sentence right here should give you a clue that it is a hypothesis test, because I'm asking you to check this at alpha equal to 0.05. Okay, if you see something like that, there's a really good chance that it's a hypothesis test. Okay, but again, in this case, what we're doing is we're making a statement that the target value is 6 millimeters, and now we're checking on that statement, basically. Okay, so this is a hypothesis test. It is a one sample hypothesis test because basically what we've done is I've said we've got a parameter which is our mean. My null value or my hypothesized value is that the mean is equal to 6. Okay, it doesn't talk about two samples. It doesn't talk about k samples. It doesn't talk about anything like that. In order to get to a two sample hypothesis or beyond, somewhere something has to be talked about with multiple parameters. And in this case, we're only talking about one. Okay? Now, the first thing that we're going to need to do, okay, so we know this is a one sample hypothesis test. Okay? We also know that the hypothesized mean is 6. Okay, 6 millimeters. Now, the things we have to decide from here R. What's our alternative? Okay, which is HA. Okay, we also have to decide alpha, which we were given. Okay, we also have to decide the type of distribution to use. Okay, now hopefully in this case we will use either Z or T. Okay, length doesn't really get us to a binomial distribution or Poisson or anything like that. Okay, it's going to be continuous, so we're hoping to use Z or T. I'll talk a little bit about how you decide on which. Okay, so once we decide that, we'll get to the rest. So our alternative in this case, we have three alternatives. It can be less than, it can be greater than, it can be not equal to. In order to determine the alternative, you really have to take it from the question. Okay? The question might say, are the mean lengths too long? Are the mean lengths too short? Is the mean no longer this value? Does the assumption hold? Different things like that. That's where you're going to figure it out. Anytime you see a question that is worded like, is the mean equal to 6? Okay? If it's asking you for an equal, we know an equal can never be in the alternative. Only a not equal. Okay? Equal has to be in the null. Okay? Remember, you'll never know equal unless you have the full population. So what we're really doing for all hypothesis testing is we're basically saying, this is what I think. Now I'm going to collect information to try to refute what I just said. Okay? We can never accept the null. We can only reject it or fail to reject it. Think about it kind of like a jury trial in the United States. Okay? Innocent until proven guilty. Okay? And we only conclude guilty or not guilty. We really, even if we conclude not guilty, we don't know for sure they're innocent. Okay? So all we can conclude is there enough evidence to say that they're guilty? It's the same idea with hypothesis testing. So we know our alternative is going to be not equal. Okay? We know that alpha is 0.05. Okay? Now let's talk about the type of distribution. Okay, here is the easy way to think about it. Let's do it this way. If the data comes from a normal distribution and you don't know sigma, okay, then we use T. Okay? Now, don't get fooled. In order to use Z, the problem has to specifically state the historical variance is this. Historically, we know the variance is this. We expect the variance to be this. That kind of thing. If you're just given a sample, then you don't know the true sigma. If you're given sample statistics, you don't know the true sigma. Okay? Let's go back to our problem. It says here, engineer is doing the study. The sample he collected is in the worksheet called staples. Assume the target value is 6. Okay? So, nothing in here has said anything about the true variance, the historical variance, any of that. It just said, here's some data. Here's some data means you're going to calculate the sample mean, N, and the sample variance or sample standard deviation from it. That means for this problem, we will use T, assuming one more thing, since we don't know sigma. Okay? Now, we need one more thing, as long as the data comes from a normal distribution. Okay? So, first thing we need to check is, does the data come from a normal distribution? Okay? Now, we have a couple ways we can do that. We can do it with a normal probability plot, or we can do it with a normality test. Okay? StatHelper will show you both. So let's go take a look. First, let's look at the data. Here's the data, okay? I put the data into Excel because Excel, the stat helper will take Excel, okay? So I put everything into Excel. And if anybody wants, I will post a link to this data. Okay, you need to just let me know. Okay, so here's the data. I'm going to go back to Stat Helper. We're going to come up here. In order to get the normality test, you're going to do that from descriptive statistics. Okay, so what we're going to do here is we're going to click Start. We're going to open this box. We need to go collect the file to upload. And we do that. Click, we go find it just like any other file upload. I've got it under data sets. Okay, now here you're going to select which sheet it's on. My sheet is called Staples, so I'm going to select Staples. Here you're going to tell it which variable. When you create these files, you have to give it a label. Okay, it has to have a label in the first cell. Okay, so I've got length for Staples. On the Staples sheet, I'm using alpha equal to 0.05. Now I can click Run. Okay. Under the Work tab, it'll give you all the work for your usual summary statistics. Mean, variance, median, range, things like that. What we're interested in is the normal probability plot. Okay? We come here, we can see that the p-value for our normality test is 0.7257. Okay? When you test for normality, what you're doing is you're looking to see if the p-value is bigger than alpha. If it is, then you're okay to assume normality. In this particular case, since it is bigger than alpha, we're going to assume the data comes from a normal. The other way we can do this is basically by just looking to see how the data hugs this 45-degree line. Since it works fairly well, okay, we're going to assume normality. Now, one more thing about this p-value versus the graph. I would, when you're first looking at these types of graphs, a lot of times you can look at things and say, well, it doesn't really look like everything hugs the line. Okay, you have to be very careful of looking for things that aren't there. Okay, this is why it's nice to have the test with it. The p-value test says 0.7257. That is a really large p-value. Okay, so what that tells us is that this data actually does a really good job hugging the line. Okay, for you to get something that's not normal, you would have to see like a pattern, or you would have to see points way off the line. Okay, in this case, we're good to go. Okay, so if we come back here, we can basically say we will use t since we don't know sigma, and okay, the data comes from a normal distribution. Okay, we have those two things. So now what I'm going to do is I'm going to come here, I'm going to go up to hypothesis tests, okay? Then I'm going to go find one mean with t. Notice we have one mean with z as well, but we already showed that it came from a normal, and we know that we don't know the standard deviation, okay? So we're here with one mean t. I'm going to click Start. I'm going to go with raw data. And by the way, you don't necessarily have to use the stat helper for these things. I'm doing it because it shows you the work, and then you can see how these things are done. But you can use any package will do these types of hypothesis tests and such. Minitab will do it. Jump will do it. SAS will do it. R will do it. You may even be able to do this in Excel. I don't know for sure. I'm sure there's some add-ons with Excel. So don't feel like, okay, I have to do this with the stat helper. You don't, okay? But the stat helper makes it nice. Okay, so notice we have two different options here. You can use summarized data if you knew the sample mean, sample variance, etc. Or you can use raw data because we have the data in a file, okay? So we're going to come here to Browse. I'm going to go find my file, just like I did earlier. I'm going to pick my data sheet, which is Staples. I'm going to pick my variable, which is length. Okay, so we've got our data in. Now we need to tell it some of these other things. Our hypothesized mean was 6. If you recall from the problem, hypothesized mean is 6. Okay, and our alpha value is 0.05. And finally down here, we can click this drop down and decide what our alternative is. Is it not equal? Is it greater than? Is it less than? We can see here, based on what we saw, our hypothesized value, or hypothesized, is going to be not equal to, or direction, if you want to look at it that way. So we're going to leave this as is, as not equal to. So we've got our data in. We know our hypothesized mean. Okay, we know alpha. We put in our alternative. Now let's just click run. Okay, so what you see here, our null is 6. Mu is equal to 6. Our alternative is that it's not equal to 6. Here's the formula for the t-test. Okay, notice this looks very similar to the z-score we just talked about. Okay, x bar minus mu. The difference is here, instead of sigma, we have s. Okay, so now all we're going to do here is we're going to play plug and chug. Okay, notice it says here the descriptive statistics tab. We can come over here and click, and it gives us that information: sample size, mean, standard deviation, etc. Okay, here's our t-statistic. Now, I'm not going to go in great detail on how the p-value is calculated. If anybody wants to know that, okay, or they want more information about that, please contact me directly, okay, and I will, or post a question in the comments, and I will get you some information on how that works, okay. But this is the calculation for the p-value. Notice here, all we're doing is basically finding, we would be using a t-table to find this probability, okay? Now, you might be thinking, well, we just used the z-table to do it. We should be able to do it, right? And the answer is yes, but now that we have this degrees of freedom that we have to deal with, we would basically need a different table for degrees of freedom, for each set of degrees of freedom. So normally what happens is you will use the computer to find this. We usually will not be doing this by hand with a table. Okay, so we get our p-value of 0.0372. Okay. So our p-value, 0.0372. Let's just make sure. 0.0372. Now, what we have to do now is we have to decide what is our choice. Are we going to fail to reject, or are we going to reject? Okay, well, come up here. This is an interpretation tab. This tells you what to do. You reject if the p-value is less than or equal to alpha. Fail to reject if it's greater than. Our p-value is 0.0372. Alpha is 0.05. We can see that 0.0372 is indeed less than alpha. So we will reject, okay? So since this is less than 0.05, okay, we will reject the null, okay? All right, great. So let's go back here. What does that actually mean? Well, if we go back to the work, we're going to come up here and we're going to say, I'm rejecting the null that mu is equal to 6, in favor of the alternative that the mean is not equal to 6. Okay, so think about what we've done so far. This is what I like to call the real world question. What do they want to know? They want to know, does the assumption still hold? Okay, then we turn this into a statistical question, and the statistical question became the null, the mu is equal to 6. The alternative is the mu is not equal to 6. Let's run that test. Okay, then we went through and ran the test, and we found the statistical answer. And the statistical answer was, since the p-value is 0.0372 is less than 0.05, we're going to reject the null and say the mean is no longer equal to 6. Now what we want to do is go back to the question and put it back into the context. So, since the mean is no longer equal to 6, then we can assume that the assumption no longer holds. Okay? So we reject the null, therefore assumption no longer holds. Okay? And I equate that to a real world answer, right? I mean, if you're really doing this for somebody, they're not just going to want to hear reject the null. What they're going to want to know is, okay, what does that mean to me? Okay, you want to put this in some sort of a setting that your audience understands the worth. What are you trying to do beyond just talking about some Greek letters? Okay, what we were trying to do here is we were trying to understand if the assumption that the target value for staple mean length is still 6 millimeters. And the answer is, based on our test, that assumption does not hold. Okay, any questions on what I just did? Deciding on the alternative, deciding on the hypotheses, deciding whether to use Z or T when it's a one sample test, how you interpret the p-value results, and then essentially how you bring the answer from the statistical realm back into the real world. If there are any questions, please post in the chat, and I'll wait a couple of minutes. And I think this is your typical one sample hypothesis test type question. I feel like the hardest things to deal with in here is, what's your alternative? Can you go to the question and pull it out? And then, should you be using Z or T? Because whether you use Z or T is really just about which test statistic to use, right? I mean, how you go about it from there really doesn't change. Okay, you're still going to find the p-value, you're still going to make your decision, and you're still going to bring everything back to the real world. Okay, so I don't seem to see any fires going on in the chat, so I'm gonna assume everything seems to be fine. And again, once I'm done with question number 4, I will hang out for a little while for questions and answers. It could be on these 4 questions. It could just be statistical things in general. Okay, so let's do the last question. You can see how burnt my head is. My son had a football game. It just, I mean, I'll never understand why when they build these facilities, they have to put the silver metal bleachers with the sun beating down on them. But at any rate, okay, so here is the last question. All right, so what we've seen so far, we've seen a normal distribution problem, we've seen a sampling distribution problem, we've seen a one sample hypothesis test type problem. Now what we're going to do is we're going to dive into a little more of a complicated situation. Okay, so fusible inner linings are being used with increasing frequency to support outer fabrics and improve the shape and drape of various pieces of clothing. The accompanying data, okay, and I'll show you where that is, on extensibility, okay, at 100 grams per centimeters for both high quality and poor quality fabric is given on a sheet called extensibility. Okay, so let's go take a look at that before we even get to the questions. Okay, here is extensibility. All right, so you can see we have 2 columns here. We have high quality extensibility and then poor quality extensibility. Okay, now let's go back here just for a second. So we said we had high quality, which is H, poor quality, which is P. Now, you see this data. One question I get all the time from students, and some not students, is, okay, my sample sizes are not equal. Okay, is that going to make for a bad test? Or can I still run the test I want to run? And the answer is yes, you can still run it. what's going to happen here is your standard deviation, when you put it together for the two samples, is going to be a little lopsided in terms of the larger sample. Okay, it's going to be more precise because remember, when we look at standard error of a mean, again, is sigma over the square root of n. So when you have an n equal to 8 versus an n equal to 24, okay, that standard error based on the n of 24 is going to be more precise. So we do have to be aware of that, but you can still do the test like you normally would. Okay, so we've got two samples here. We know this is going to be a two-sample test. Okay, two samples, which leads us to a two-sample test. Okay, and in this case, we can already see based on the problem, we're going to be testing means. So it's going to be a two-sample mean difference test. Now, the reason that I know it's going to be a mean difference is because you can see here they're basically saying to test the alternative that mu1 is not equal to mu2. That means our null is going to be mu1 equal to mu2. And if you think about that, we can rewrite that as mu1 minus mu2 equals 0. We can rewrite the alternative as mu1 minus mu2 not equal to 0. Okay, so we're going to look at this as a two-sample difference test, and we will write it as mu1 minus mu2. Okay, so in this particular case, okay, let's stay here. In this particular case, our alternative hypothesis is going to be not equal. Okay. Alpha, again, 0.05. Okay, so we have some questions we have to answer. First, are these populations independent or dependent? Okay, that's the first question. Second question is going to be, let's do it like this. Second question is, are the population variances equal or not? Okay. Now, if you've come across these two sample tests before, you know if the populations are independent, we're going to use the two sample independent test. If the populations are dependent, we're going to use a paired test. Okay? We also know that if the population variances are, if the populations are independent and the population variances are equal, then we're going to use a pooled test. If they're not equal, then we're going to use an unequal test. Okay? The other thing we have to decide is, are we using Z or T? Okay? These are the three things we need to decide. The first thing we should do is decide whether the populations are independent or not. Okay? And we do that by going back to the question. Now, in order for a population to be dependent, then what we're basically saying is the experimental unit doesn't change between treatments. Okay? You see a lot of clinical trials where this happens because you're dealing with people. So what happens is you apply both treatments to the same person. An easy way to think about that is, let's say you're testing two different types of sunscreen. Okay? What you end up doing is taking each person and you put sunscreen type A on your left arm and sunscreen type B on your right arm. Okay? We would consider that paired because each person is getting both types of sunscreen. Okay? Anytime that experimental unit doesn't change across the two treatments, then we call that paired. Also, by the way, in order to be a paired test, the sample sizes have to be equal because both treatments have to be able to be applied to each experimental unit. Okay? So even if you don't really understand what's going on with this problem, you should be able to come here and say, okay, based on this data, these are not paired, okay, because they're not equal. But if we want to look at it in terms of the problem, okay, we're taking a sample of high quality cloth and comparing it to a sample of poor quality cloth. So there's no way they're going to be the same, okay, in terms of we're not making treatments on one piece of cloth in both treatments. We're literally creating high quality cloth and poor quality cloth. So that's independent, okay? So we are going to assume independence. Okay, now we're going to decide are the populations equal or not. We will do that once we get in, and we will do that with what we call an F-test. Okay, but before we can get to that, we need to decide on Z or T. Well, before we can decide on Z or T, we need to know, are both samples normal? Okay. Since we decided on independence, now we're going to look at normality. Okay? Now, remember, just like with the one sample test, in order to use Z, not only do we need to know that both samples are independent, we need to know the population variances for both populations. We can come up here, and nowhere here does it talk about historical variances. We expect the variances to be this. Based on history, this is the variance. Based on long-term data, this is the variance. We hear none of that. So what we're going to assume is that we don't know the variances. Okay? So we can come here and say, variances are not known. Okay? That's one. The next part of this that we need to know are the samples, do they come from a normal distribution? Okay? So in order to figure that out, we're going to go back to the software and test both samples. Okay, so we're going to come here. We're going to go back to descriptive statistics. I'm going to go to reset the inputs. Okay, I'm going to go to start. Okay, I'm going to pick data sets. Now we need to check both. So I'm going to go to extensibility. I'm going to click on, we're going to do H first. Click run. Okay, we can see here, click the normal probability plot, and you can see that the p-value for the normality test for the high quality is 0.436, which is bigger than 0.05. So the high quality comes from a normal. Now let's check the other one. Click reset, go to start, go back and get our data again. Go to extensibility. Now instead of using H, we're going to use P. Click run. Go to the normal probability plot. Now here we're getting 0.3394. Now notice one thing. You can see based on this plot there's a lot less data than what we saw in the plot for high quality. But our p-value still is 0.3394. So we're going to say yes, they're both normal. So the answer is yes. And we can come up here and say the variance is not normal, or excuse me, the variances are unknown, but the distribution for both is normal. Okay, so we know that the variances are not normal, or excuse me, we know the variances are not known. We know the distributions are normal. So based off of that, we will use T. Okay, so we're going to use T. We know that they're independent. Okay, so what we're going to use here is we're going to use a two-sample independent t-test. Okay, that's what we're going to use here. Okay, now we know we're going to use this. Okay, from here, what we're going to do is we're going to go back in here. The one thing we haven't done yet, since we have a two-sample independent t-test, we need to know if the populations are independent, or excuse me, if the population variances are equal or not. We know they're not known, but we can actually run a test to see if they're equal. Okay, so let's go back to the software. We're going to go to hypothesis tests. In order to do this, we're going to do two variances. Okay, and those two variances is what we call, We're checking to see if they're equal. We call this an f-test. So what I'm going to do is I'm going to click Start. I have raw data. Okay, let's go find the file. Okay, I'm going to choose extensibility. Okay, sample 1 I'm going to choose H. Sample 2 I'm going to choose P. So I'm comparing high quality fabric, okay, basically to the low quality fabric, okay, or poor quality fabric. Now, does it matter whether you do P in the first sample or H in the first sample? No, because we're looking for inequality, or excuse me, we're looking for not equal to anyway, so it doesn't really matter. Okay, we have alpha to 0.05. Our input hypothesized ratio is going to be 1, because when you do an f-test, it's basically the you're finding the quotient of the two variances, and when we subtract them, equality means 0. When we divide them, equality means 1. Okay, we want not equal to. Let's click Run. Okay, here's our hypothesis test. Now, if you want to understand what's going on with the two sample variance test, you can go through it right here. We have introduction, description, and all that other fun stuff for this. What we're going to do is we're going to go down here. Okay, we can see here's our p-value. I'm going to go over to interpretation. And based on this, we're basically saying because 0.4863 is greater than 0.05, we're going to fail to reject, which means we're going to assume equal variance. Okay. Let's go back here. And now we assume equal variance. So what we're going to do is we're going to do a two-sample independent t-test assuming equal variance. Okay. Now that we have this, we're going to go back to the software. Okay. Remember, we tested equality of both samples. We tested equal variance of the two variances. Okay. Now we're going to come here. We're going to choose two means independent test. Okay. So we're going to click Start. Now, there's a whole lot of things going on this one because there's so many different things to input. Now, luckily, we don't have to deal with this because we have raw data. Okay. Go back, find where your data set is, choose the right sheet. We want H versus P. Again, high quality versus poor. Again, because the alternative is not equal to, it doesn't really matter whether you put H first or P first. Okay. We're going to have H first here. We're going to have P second. I'm going to come over here. My hypothesized difference is 0. We know that's the case because we want to test for equal to 0, or we want to test mu1 equal to mu2 versus mu1 not equal to mu2. So we need the hypothesized difference to be 0. Alpha equals to 0.05. Our alternative is going to be not equal to. Our variance assumption is going to be equal variance. Okay, we found that out based on the f-test that we did. Okay, so we have our samples in place. We have alpha, we have our hypothesized difference, we have our alternative hypothesis, and assuming equal variance. So we've got everything in there. Okay, we're going to go and click Run. Now you can see here, we have our null and our alternative. Here is our t-statistic. So if you think about the way the one sample was set up, it was x bar minus mu over the standard error. This is essentially the same thing. X bar 1 minus x bar 2 minus delta 0. But delta 0 in this case is just going to be 0. So this is just going to go away. And then divide by our standard error. Okay. We know we have equal variances because we already did this. Okay. So what we're going to do is we're going to use what we call a pooled standard error. Okay. That's what this S of P is. Because we assumed equal variance, we're going to use this S of P. So we calculate this S of P based on what you see here. Play plug and chug into the standard error. Now we play plug and chug into the t-statistic. We find our t-statistic to be 0.4164 negative. We have 30 degrees of freedom. Then we're going to just go back to the t-distribution, plug these two things in, and find our p-value. Again, same thing. Because the t-distribution is dependent on degrees of freedom, you typically will not do this with a table. You're going to do this with a computer. Okay? So we find our p-value to be 0.6801. And when we do that, what ends up happening is we come up here to our interpretation tab, and we find that since 0.6801 is greater than 0.05, we're going to fail to reject. Okay? And conclude that there's not enough evidence to support our claim. If we take this and go back to the question, okay, what we're basically saying is there's not enough evidence to conclude that the mean extensibility for high quality is different than the mean extensibility for poor quality cloth. Okay? So what we've done literally is part A and part B to this question. Okay? So remember the things you have to check for this two-sample t-test. You have to check, are you dealing with independent or dependent? You have to check, are the population variances equal or not? You have to check, do the samples come from a normal distribution? And then, are you going to use Z or T? And then you basically run the test from there. Okay, woo, that's a lot. Okay? But those are the things you need to make sure of before you choose the test you're going to run. Now let's go back up to the question. Now the question says create a 95% confidence interval for that mean difference and use it to test the hypothesis from part B. Now, you can always use confidence intervals to test hypotheses. What you're going to do is calculate the interval, and then you're going to see if your hypothesized value falls in there. That's a mouthful. Okay? If it does, then you're going to fail to reject. If it doesn't, then you're going to reject. Okay? So in our case, what we're going to do based on this hypothesized value, which is 0, is I'm going to create the confidence interval, and then I'm going to look to see if 0 falls in there. And if it does, I'm going to fail to reject. If it doesn't, then I'm going to reject. Okay? So let's try that. Let's click on confidence intervals. Notice here we have a whole bunch of different ones. But since we already checked all of that stuff when we did the hypothesis test, all of this comes back to us for the confidence interval. So we still know that both distributions are normal. We still know that variances are equal. We still know that we want to use T. And we still know that the two distributions are independent, or the two random variables are independent. So we will still use two means independent. Okay? We'll come here. We'll pick raw data. Find our data again. We're going to choose extensibility. Again, we'll keep the first one H and the second one P. So you notice the tab box to the right, or the box to the right, all the same as what we did when we did the hypothesis test. Now come over here. Our confidence level, we choose 95. Why? Because alpha is 0.05. Remember, confidence is always 1 minus alpha. Okay? Now we choose the type of interval we want. Well, we could choose two-sided, one-sided lower, one-sided upper. Because our alternative is not equal, then we want a two-sided interval. We care about it being outside the low or outside the high. Okay? So we want to create an interval there. Okay? We still have to get our variance assumption. In this particular case, we proved that the variances were equal, so we're going to assume equal variance. So technically, the only difference between what we did for the hypothesis test and what we're going to do here is, instead of choosing alpha, we choose confidence level. And instead of choosing alternative, we choose which type of interval do you want to create. Okay? Everything else is the same. And you shouldn't be surprised by that, because confidence intervals and hypothesis tests are kind of like are analogous to each other, right? They all start out with that probability assumption that inside the Z of alpha and 1 minus alpha, your probability should be 1 minus alpha. Okay, so it all works out to the same thing. So unless I did something wrong, which I hope I didn't, we should fail to reject. Okay, let's find out. Okay, so what this does is basically tells you exactly how to calculate the interval. This is all here if you want to go and take a look at it. Okay, we find that our interval is negative 0.683, or negative 0.4683 to positive 0.3083. Now, what did we say? I said, take our hypothesized value, which in this case was 0. See if it falls in the confidence interval. Does 0 fall in? And the answer is yes. Okay, so because 0 falls in, we will fail to reject. Okay, now one more thing I want to make very clear about confidence intervals. What I just did is not an interpretation of a confidence interval. All I did was use a confidence interval to run a hypothesis test. Okay, if you're asked for the interpretation of a confidence interval, then you should come up here and you should basically go to interpretation and say, we're 95% confident that the true mean difference is between negative 0.4683 and 0.3083. So when you deal with an interval for a an interpretation for a confidence interval, you need two things. We need the level of confidence and you need the range. Okay, that's an interpretation. If you're asked to decide on a hypothesis test, what you're going to do is find your hypothesized value, which was 0. See if it falls in the interval. If it does, you're going to fail to reject. If it doesn't, then you're going to reject. Okay, so let's go back to this question. So, part C was create the confidence interval, which we did. Use it to test the hypothesis from part B, which we did. We did find that they matched, thank God. Okay, and also think about this. They should never not match. The only time that it should remotely come close to not matching, and this should only be based on rounding errors, is if you found something that gave you a p-value, say alpha was 0.05, and you found a p-value of like 0.04999 or 0.05111, or something really, really, really close to 0.05. And then based on rounding, they may not match, but I would say 99 point however many %, of the time, it should always match. Okay, and here's the other thing. If you get something where your p-value is that close to alpha, you should not be deciding to reject. Okay, it's way too close. Remember, p-values are random variables. So nobody would say if I got a p-value of 0.04999, nobody would say that I'm confident that if I took another sample, I would get another p-value that's below 0.05. Okay, so you're kind of in that no man's land range. Okay, with significance. You should always be thinking of erring on the side of caution, making some statement when you're really close in that gray area. Okay? Okay, so let's stop right there. What we basically done is we've done 4 problems. The first one was really dealing with normal distributions, how you find probabilities, how you find an x value that corresponds to a probability. Then we talked a little bit about some sampling distributions with the central limit theorem, how you deal with distributions that are not normal. Can you use central limit theorem to find probabilities? Then we talked about a one sample test. We talked about the idea, how do you identify that it's one sample? How do you identify whether you should be using Z or T? Then running through the test, making your decision at the end. And then finally, for the last problem, we talked about, we've got 2 samples. What do we have to do to get to the test we're going to use, right? We have to test for normality for each sample. We have to decide, are they independent or not independent? We have to decide, are the variances equal? Then we decide, are we going to use Z or T? Okay. Then once we decide all of that, then we can actually run the test. We draw our conclusion and we bring it back to the real world. We also saw in the same situation that we could create a confidence interval. And we could use that confidence interval to make a decision on a hypothesis or give us an idea of what the true value of that mean difference could be. Okay? A lot of times in the real world, when you reject, okay, so let's say that we go back to problem 3 and I say, because the p-value is less than alpha, I'm going to reject and say no longer is the mean equal to 6. Okay? So the next question somebody's going to ask you is, well, if it's not equal to 6, then what is it equal to? And that's where a confidence interval could come in. Okay? You could create a confidence interval and you could say, well, I'm 95% confident that the mean is somewhere between 4 and 5. Okay? So confidence intervals are very nice because not only can you test hypotheses with them, but you can also give somebody a range of values that the parameter could take on if you fail to, if you reject the null. Okay? I can't even tell you how many times I've heard somebody say, well, if it's not 6, then what is it? And I say, well, I'm 95% confident of this. And then they say, well, what do you mean by 95% confident? So there's all of that to deal with as well. There's so many disciplines that, you have a toolbox, you have a problem, you take the tools in your toolbox and you solve the problem, and there's one answer, okay? And statistics is not like that. Statistics is very gray, okay? And a lot of people don't like that, okay? You have to really be able to make people understand that, listen, we're doing it this way because we only have a sample. I can only give you my best estimate for all of this. We can put some error on that estimate, and we can make inference to give an idea how confident we are, but that's all we can do, okay? So sometimes it takes people getting used to that kind of, I don't want to say manipulation of the data, but just using sample data and not being able to come up with a 100% confident answer. Okay, so it's about 7:40. We've got some time left. What I wanted to do is we did the 4 problems. I wanted to open it up a little bit for some question and answer with the chat. If anybody would like to, questions on the actual problems that I did, or just, questions on any of the statistical things in general. Or even just anything you'd like me to talk to on, in terms of, statistical problems, homework problems, test type things, any of that. Okay, so it seems like I'm not getting anything in the chat, so it seems like there aren't any questions. So what I'll do is we'll end for the night. If anybody does have any questions in terms of any of the things that I've done during the week, or just in general, post it in the comments. Send me a question to statprof5000@gmail.com. I'll post that in the comments as well. But other than that, everybody have a good night.